we have speaker from Leiden University, Pooneh Nazari. She's from, I did from your website, from small town in Iran. And then she went to UK in St. Andrews.
Yes.
For undergrad, and then she worked, and then you also worked in University of Cambridge with Kathy Clark, and then she's doing a PhD with in Leiden with Avina van Dishok, and she's interested in this star and planet formation, especially astrochemistry. So we're here to talk today. Now the floor is yours.
No, thank you so much for the very nice introduction. So I'm Pooneh Nazari, and I'm a PhD at Leiden with Avina, and today I'm going to talk about complex organic molecules around low and high mass protostars. So complex organic molecules are these species which have at least 6 atoms, and they include carbon in there. So I'm going to start with this brief. Oh, it was working before.
Maybe you can.
I can just use this. So they are these species that they have. Let me start with this broad picture of how planetary systems form. But without going into any more details, I'm going to focus on the protostellar phase, which is where we think that planets start forming. So it's important to understand the chemistry and physical conditions of this phase to understand the chemistry of planets. And I'm going to focus on 2 questions. The first one is that whether complex organic molecules or comps form in the gas or ice. We know methanol forms in the ice, but what about the others? And the second question is why not all protostars show millimeter comb emission? Starting with the first one. So to answer whether comps form in the gas or ice, we need to ask another question. How similar are abundances of these species from source to source? And to answer that question, we need to have a large sample of sources. However, large sample of sources with ALMA are missing. And ALMA really traces these inner regions around the protostar where the temperatures are quite warm. So these molecules can sublimate into the gas, and that's how we see them. But far from the protostar where the temperatures are quite cold, these molecules would be in ices, and that's what JWST would be able to trace. However, for this talk, I'm going to only focus on ALMA observations. And the reason that I'm emphasizing on the ALMA part is that we need the high angular resolution of ALMA to be able to obviously resolve these sources. But more importantly, we need high sensitivity. And the reason is that we want to observe the optically thin isotopologues of the most abundant species, such as methanol, which usually have optically thick lines. And as I said, we need large samples. To achieve that, we went to the ALMA-GAL large program, which is this wonderful survey that looked at around 1,000 dense clumps scattered throughout the galaxy. And what we did was that we picked 40 line-rich sources out of the sample. And when I say line-rich, it means that we really detected the rarer molecules in more than 30 sources. Because before this study, when people said that, we look at 20 line-rich sources, they meant that they only detect methanol in 20 sources, but the other molecules were detected in maybe 5 or 6. So this is really the first study that looks at this problem sort of statistically, and looks at the statistically significant sample of sources. And what I did was that I focused on M-bearing complex organic molecules, and Martijn van Gelder, which is another PhD in our Avina's group, looked at methanol deuteration. Here, so this is a very nice paper. I recommend you to take a look at it. But for this talk, I'm going to only focus on M-bearing complex organic molecules. Here, I'm showing the spectra of some of these sources that I looked at. And what we wanted to do is to fit these spectra and find the column densities and excitation temperatures of some species. And the species that I focused on are sort of shown here. I've highlighted CH3 and H2 because this molecule was only detected in around 5 sources before ALMA-GAL, and we detected it in an additional 12 sources. So it's already more than doubling the number of detections, which is nice. And then I've also highlighted the other 3 to say that we really use the optically thin isotopologues of these molecules to find their column densities. Here I'm showing an example of CH313 CN lines toward one of our sources. And the black shows the data, the red shows the Cassis model. So we use Cassis to feed these spectra. And what we find is column density and excitation temperature. So now let's see what we found. Here I'm showing the average excitation temperature of our molecules for all the sources that we could measure the excitation temperature. So each data point is really the averages what we see in multiple sources. And we see a trend, and well, there is something here, but what I was saying here is that these molecules are ordered by the sublimation temperature. And what we are seeing is that the molecules with the highest sublimation temperature also have the highest excitation temperature, which could probably sort of suggest that we have this sort of onion-like structure, where some of these molecules are tracing the most inner regions around the protostar where it's hotter, and some of these molecules tracing the outer regions of the hot core where it's colder. I should emphasize that these are not extended emissions, still the hot core, but it's just we think that probably this temperature structure suggests this sort of onion-like structure.
Sorry, you mentioned you get the column density as well. Is the area that applies to resolved?
Yes, so that's a very good question. Yes, yeah. So unfortunately, at the time that we were doing this project, we did not have high angular resolution data of AlmaGal yet available. So AlmaGal has three resolution, so 5 arcsecond, 1 arcsecond, and 0.3 arcsecond or so. So we were using the 1 arcsecond one, and now the 0.3 arcsecond is also available. So I've looked at a few sources, and yes, we do have this. Well, okay, it's not as beautiful as this onion-like structure, but we do have like formamide tracing the inner regions and the other tracing the outer regions. Yeah, but at the time we didn't have the high angular resolution data. So yeah, so this was the temperature. Now let's look at the column densities. So this is the column density, a plot that shows the ratio of ethyl cyanide to methyl cyanide, C2H5CN to CH3CN, as a function of luminosity. And these are the sources that they were available before AlmaGal with ALMA. So there are like around 10 sources or so. Now let's add more than 30 sources to this plot. So these are the AlmaGal sources now, and you can see that this ratio is remarkably constant, no matter the mass of these protostars or their luminosity. So there is like a 7 order of magnitude difference between the luminosities of these sources. And another interesting thing is that some of these are from the literature, and they also fall on the same distribution. So these are done by different people, different analysis, different observations. So it's really remarkable to me that how constant this is. But what about the other, like column density ratio? So I'm only showing you one here. So here now we can see isocyanic acid to CH3CN, so HNCO to CH3CN. And again, this is quite constant, but the scatter is somewhat larger. Maybe not a lot, but it's a bit larger. And what I did then was to look at all the different combinations of column density ratios for different molecules and measure the scatter, it's sort of the standard deviation. And I'm showing it here now. So this spread factor is a measure of standard deviation. So for example, 2.5 means that there is a scatter of a factor 2.5 around the mean, something like that. And like more mathematically, it's basically 10 to the dex is equal to, for example, 2.5, if you want to know. So yeah. So these are all the different column density ratios. And what we see is that, well, they are not all the same. Some of them are quite high, but which I will talk about them in a bit, but most of them are quite low. So most of them have a spread of less than factor 2.5 around the mean. And then the question is, so what does this tell us? That these ratios are very constant. It probably means that these molecules formed in a phase of star formation where the physical conditions were similar between different sources. And that phase is not the protostellar phase, because I just showed you that there were like 7 orders of magnitude difference in the luminosities of the sources that I was looking at. it's probably the prestellar phase, where we think that these molecules formed as ices. And a similar conclusion was also made by Coletta et al. 2020 for a few highly abundant OCOMs based on single dish observations. And so probably they form in the prestellar phase, but still they're not all the same. Like still, I was wondering why do we have these differences? And to like try to understand why we had these differences, I went to chemical models of Rob Garrett, so Garrett 2022, and what they are, basically they have these chemical models that it has two phases. So the first phase is the collapse phase. It's similar to the prestellar phase, so they keep their temperature at 10 Kelvin and increase the density. And then they have a warm-up phase where they keep the density constant, increase the temperature. So I said if these are very, very low spread, meaning they form in the prestellar phase, I should only use the prestellar phase of their chemical models. So I went there and looked at what they were finding in ice when they were forming these molecules in the ice. And what I found is, well, they are changing as a function of time. So these abundances of these molecules change as a function of time. And then I was like, okay, so if they've changed as a function of time, I can probably translate this spread in the column density ratios to a spread in prestellar lifetimes. And when I do that calculation, I find that this sort of time spread, the spread in prestellar lifetimes, is basically constant no matter what column density ratio I use. And that's exactly what I expect because I'm looking at the same protostars. So their prestellar phase, the spread in their prestellar phase lifetime should be the same no matter what column density ratio I use. So this is nice, but again, I should say that I really used a simple toy model to do this. This needs to be followed up with proper chemical models.
So what's the basic idea? How do you get a time scale from the density ratio?
Yes, so I mean, I can later maybe show you the proper mathematical things, but so I did a very simple thing. I basically just went and saw that the abundances change as a function of time in the prestellar phase, and I tried to fit a very simple toy model to this, a very simple mathematical relation, and then I just basically so then I had basically I had the abundances as a function of time. I could then translate the spread in the condensate ratios to the time.
The idea is that these are non-equilibrium abundances. They're evolving.
Yes, definitely. They are evolving, but obviously the atoms are conserved in that sense.
But sorry, this requires that you know timescales in the prestellar phase to what accuracy and by what other metric?
Yeah. So the only thing is that here I'm really looking at time spread. So I can't, with these information, I won't be able to tell you what is the prestellar time. So I can't really say what is exactly the time. People think that it's around 10 to the, I think it's between 10 to the 4 and 10 to the 5 years.
Sorry, but the method you were just describing, you were fitting something as a function of time?
The abundances of these molecules.
But what was setting how did you get time on that you were fitting against?
So these are just, they're based on chemical models and.
Okay.
Yeah, all I did, I was just fitting their graph.
I got it.
Yeah, I didn't do any
complicated
chemistry there, yes. Yes.
But is there abundance ratio, say, growing or decreasing monotonically?
Yeah, so
and also with a lot of scattering, right?
Yeah, so that's the thing. So in the ice, in the prestellar phase, because when these molecules form in the ice, usually that's why I made this simple toy model. So usually the abundances just increase and they become constant at some point. But then they have this sort of increase, and that's why you get this sort of small scatter, so like a factor 2 in the prestellar lifetime.
So the abundance ratio you see are not their equilibrium value.
Oh yeah, so they're maybe this is what you were asking. So but yeah, so that they're not necessarily at equilibrium at the time. You know what I mean? So they are changing as a function of time.
They're changing.
They are changing as a function of, and that's why I can't do this calculation. If they weren't changing, it wasn't possible to do that. So yeah, but again, this is a simple toy model. I want to again emphasize that. And maybe like another way of saying it might be better, which is more general, to say that some sort of scatter in the pre-cell physical conditions, like temperature or density and stuff like that, could cause this. But if this time idea has any truth to it, it's interesting because we are seeing that these the mean of column density ratios are the same for low mass and high mass protostars. And that could mean, I can't again tell you what is the pre-stellar lifetime, but what I can say is that they're both part of the same time distribution. So high mass protostars and low mass protostars would have similar pre-stellar lifetimes. I don't know what that number is, but would be similar if the time like theory is correct. And then if they are similar, so high mass and high mass pre-stellar phase and low mass pre-stellar phase is similar, then probably points to the competitive accretion theory of high mass star formation, because then it would be high mass protostar would be forming from like a bunch of low mass protostars that they would aggregate to form one big one. So yeah, that was the sort of conclusion that we made there. And yeah, so are there any further questions here, or should I just? Yes.
What is the evidence that those are high mass protostars?
Yeah, that's a good question. So ALMA mainly targeted high mass clumps, but the reason is mainly the luminosities.
Are these all the same distance? So, and it's clear that they're not much larger, like.
Yeah, so they are not all the same distance. So they are they are mainly, most of the sources that I'm showing here are around 4 to 5 kiloparsecs, something like that, away from us. But there are some of them that they are at like 10 kiloparsec. So maybe 1 or 2 sources.
For the red points.
The red ones.
So what is the evidence that that's one star and they're high mass stars as opposed to a cluster of low mass stars?
Yeah. Okay. So that's true. That's a good point. But the resolution that we had here was good enough to kind of, so we even like when I was looking at this, there were like a bunch of clusters that we were seeing, and then but maybe only one core showed complex organic molecules. And it's true, if you see this again with higher angular resolution, can they again break up in more? Well, so there were 5 sources that I've checked. They didn't break up more with 0.3 angular resolution. But again, I can't say for sure.
So sorry, you said it was, so that's,
physical size, you mean?
yeah, that's still several thousand.
Yeah, that's true. So I mean, I can't say for sure.
Yeah, so I guess I'm just wondering, like, when you go across that line, are you going,
Yeah.
how different are the scales?
This is very arbitrary in the sense that I just like, we know they are for sure low mass protostars, and I was like, okay, so based on the luminosities, I just made this line. This is very arbitrary in that sense.
Just a luminosity plot.
It's just a luminosity.
But I mean, I guess, but in terms of this conclusion, right, understanding the fraction of the high mass ones that are high mass as opposed to, right,
That's
undissolved
true,
agglomerations
that's
of low mass
It's-
would seem pretty important.
Yeah, you're right. No.
You could say luminosity.
Sorry?
Yeah, more correct way to say is a higher luminosity.
Higher luminosity,
Yeah.
perhaps. And yeah, but you are right that it's possible that some of these sources could even, although we might be seeing clusters already. And I'm picking one core, for example, from that cluster, but again, that could be breaking up into more. That's completely good point. Yeah, I can't say that's not, yeah. No, that's a very good point. Yeah, but also like again, this is based on a very simple toy model. Again, I want to emphasize that. Yeah. So that was what we thought maybe is happening for that part of the plot. But then there are these bunch of data points that they have very high scatter. And just to show you like how it looks like, this is something like that. So this is, the scatter is suddenly way much larger. And it's interestingly, mainly these ratios that they had, this large scatter, they had this molecule in the NH2CHO or formamide. And then the question is, so what is happening with formamide? That always has very large ratios when you compare it with other molecules. So I want to remind you of this onion-like structure that we had Formamide is also that molecule that had the highest temperature, so probably is tracing the most inner regions. So it could have a different emitting area compared to the other molecules. And for this calculation that I did to make the column density plots, I assumed that the emitting area is the same for all these molecules. And well, obviously that assumption would be wrong if formamide is tracing a different emitting, having a different emitting area. So that's going to change the scatter. And another thing is dust. We know that dust is going to block the inner regions of the protostar the most because it's denser, basically. And again, formamide is going to be most prone to this effect, again, changing the column density ratios. So the bottom line conclusion is that both sort of source structure and potentially dust attenuation are important and need to be taken into account. Now going to the second half of my talk, which would be talking about why we don't see millimeter calm emission toward all protostars. I especially want to look at this from the angle of how dust attenuation and source structure can affect our understanding here. And to kind of say what I mean by that question, here I'm showing a plot from Vancouver at 2022, where we looked at warm methanol mass as a function of luminosity again, and we see this sort of orders of magnitude spread in warm methanol mass for low mass and high mass protostars. And then basically the question is why? Why do we see this spread? Why a lot of protostars just don't show methanol at all? And here we focus on methanol because methanol is the most abundant complex organic molecule. And if we don't see that, we don't see anything else pretty much. And so yeah, the question is why do we see this spread? And we can answer this in two ways. The first one is that there's just simply less methanol in some sources. And another way to answer this is that methanol is in these systems, but for some reason we just don't see it in the gas. And those reasons could be dust attenuation, which has already been shown in Simon et al. 2020. But what I'm going to focus here is really disks. And the reason that I say disks can have such an effect is that if we have an envelope-only protostar, what happens is that we have these sort of warm inner regions, but if this protostar has a disk, some of these warm regions are going to be cold because of this shadowing effect. And this shadowing was already observed toward this low-mass protostar, where Murillo et al. 2018 looked at the DCO plus emission, and they found that this emission is localized behind where the disk was located. And they concluded that this is because the temperature behind the disk is low, so that's why it's the best place for DCO plus to reside in. And I should say DCO plus is a molecule that can reside in cold temperatures because of this because it's D. So now I'm going to take this and say that if these are going to lower the temperature on low mass protostars, they are going to then reduce the sublimation region, and we're just going to have less methanol emission. Is this the case or not? And to answer this, I went to look at an envelope-only protostar and an envelope plus disk protostar, and then I used RADMC3D to do the radiative transfer calculations and find the temperature. So here is the temperature of my two models. We see because of this shadowing, these temperatures are quite lower for the envelope plus disk models. These are for the models that they have small dust grains. Or small millimeter opacity dust. And here are the models for large millimeter opacity dust. And again, we have this shadowing effect, but also the temperatures are a bit lower for the large dust grains. That's expected because because large dust grains just absorb the UV light less than small ones, so they are colder. And once they absorb it, they are going to emit it at longer wavelengths. Again, it's just going to be colder regions. And then what I didn't do any chemistry, so I just parameterized methanol abundance. So I just said inside so this is the snow surface of methanol. I said inside of it, it's hot, so this methanol is going to be in the gas. I just said I pretty much put the abundance constant to 10 to the minus 6. And 10 to the minus 6 value comes from, in the envelope, 10 to the minus 6. And that value comes from the ice observations of methanol. So I parameterized it and then calculated methanol emission using radiative C3D again. And now let's compare it with observations. Here I'm showing the integrated methanol flux. So this particular line integrated that line as a function of luminosity, and these are from Peaches data. So Peaches was this survey that looked at 50, I think, low mass protostars in Perseus. And yeah, so again, we are seeing this spread. So I wanted to see if I can explain the spread or not. The triangles are upper limits, circles are detections. And now let's see if the models can explain it. So these are the envelope-only models, and you can see that they cannot explain the data. Now let's add the disk. So here they do a much better job at explaining the data, but still there is this part of the parameter space where we have high luminosity sources that they don't show methanol. And then the question is, what is missing in my models so that I can't explain it? So these are only the models that they have low millimeter opacity dust. So the dust is optically thin. Now let's add high millimeter opacity dust. And again, these envelope only ones, even with high millimeter opacity, they cannot explain the data. But the disk ones can. So the conclusion is we need both disks and optically thick dust in those disks to explain this whole spread. And it's nice that these empty circles here show the sources that they have confirmed, with confirmed disks, and they all fall in the right part in the blue region. So that's nice. So yeah, that was the low mass for low mass protostars. How about the high mass protostellar disks? Can they also explain the scatter that we were seeing? So again, just to remind you, we also have this scatter around high mass protostars. Can this explain that? So I did exactly the same thing for high mass protostars, but now I added viscous heating to my disks because they are hotter, they have higher accretion rates, so I'm expecting that viscous heating is effective. So when I do that, this is the temperature structure for one of my models. Yeah, we see sort of viscous heating is effective here, so in the inner 100 AU or so. And another thing that we found is that so for low mass protostars, we have this cold midplane temperature, but here which is colder than the surface of the disk, because the surface of the disk is directly, the star is shining on it. So for here, there were some of my models that I had warmer midplane temperature than the surface. So the surface was actually colder. And this is what was suggested by observations of Barr et al. 2020, where they see these sort of infrared absorption lines. And they suggest that it probably is because we have this cold layer of gas on top of this warmer layer. So it's nice that we see this in some of our models. And we also found, so the disks are hotter, and we also found that this shadowing basically is not that effective for high mass protostars. And the combinations of these two mean that we cannot explain the data with the disk model. So these are our models, and these are the data, the integrative flux of a methanol line from Almagal survey. And yes, so we cannot explain it, especially the models do a bad job in these regions of the luminosity. Maybe they do a better job here, but still they can't explain that. And then the question is, so what is missing in the models? I should say that we did not include ultra-compact or hyper-compact H2 regions. We know that high mass protostars could have these regions where basically the gas is completely ionized and atomic, so there is no methanol there. And depending on where the methanol sublimation region is, I mean, if it's inside of this, so all the methanol in the gas is basically destroyed. But if it's outside, you could still have some methanol emission. And because of that, if it's mainly inside, you would basically lose all the methanol emission. Still, you could have methanol in the ices here, but it won't be in the gas for us to see it. And when I look at the data, it was suggested, so it's suggested, so it's not confirmed, but based on their mass and luminosity, these protostars could host a hypercompact or ultra-compact H2 region. and these sources that they are empty now, these data points. So they also fall in these regions of the parameter space, so that's quite nice in that sense. And then for these, I don't know what's happening. It could be X-ray, like basically destroying these, or it could be luminosity measurement also. But maybe H2 regions could have an effect in bringing down the methanol emission that we see. I guess we need to follow up on these sources to see like if there is an H2 region there or not. So to summarize, we looked at column density ratios of n very complex organic molecules. We found that they are very constant across sources with orders of magnitude difference in luminosity and mass. And this points to the formation of these molecules in a phase of star formation where the physical conditions are similar, probably the prestellar phase as ices. And we found that source structure, disks, and thus optical depth can explain this sort of spread that we see in methanol emission around low mass protostars, meaning that absence of methanol emission does not necessarily mean absence of methanol itself. And finally, this could not explain the lack of the spread in methanol emission around high mass protostars, and perhaps H2 regions have some sort of effect. And that's, I think, with that, I'm going to end my talk.
Thank you. And question?
So for the modeling of the high mass stars, how are you picking the masses of the central object?
So do you mean this plot?
No, that I see as luminosity, but
This
you're
is observation.
in your RADMC 3D model.
Yes. So what I'm assuming for the mass,
Mm-hmm.
So yeah, so the masses that we are assuming. So the envelope masses we are varying, and so I'm assuming between I think 50 and 1,000 and solar mass, and 50 I know it's more of an intermediate mass, but yeah, we keep it in. And then the central protostar, we just keep it constant at 30 solar masses. But I do change it. I do also run a bunch of models with lower protostar mass, but that doesn't have that much of an effect on the methanol emission that we see there. But the luminosity I changed. The luminosity goes,
So you don't have like a correlation between the luminosity and the protostellar mass in the models.
No, so what I do is that I have this range for the mass and I have a range for luminosity, and then I make sure that, so it's not a correlation in that sense. Then I make sure that, for example, for for all the masses, I have all these different luminosities. Does that make sense? For all the envelope masses, I run the models for all these.
But I mean, no, but you never change the protostar; just stays basically.
Yes, the protostar itself stays the same effective temperature, the same mass. But I do change the bolometric luminosity. If that makes sense. So
in correlation with the accretion rate, or no?
Yes. The accretion rate is related to the accretion rate actually is more related to the envelope mass than the.
But the luminosity is surely set is m times m
Yeah.
dot.
So okay, no, that's right. That's right. So yeah, I don't. No, that's correct. For the luminosity, just making sure that I'm getting things correct. The mass, the envelope mass, and the accretion rates that I'm assuming, they are consistent.
Uh-huh.
But then the luminosity itself, I just vary it. So I just assume the accretion luminosity also is part of that. You know what I mean? So I don't,
I'm saying it might be worth checking that m dot over r star is consistent with what you're assuming with the luminosity, since that's what's generating 50% of the luminosity is
coming.
Good
point. Yes.
Yeah.
Yes.
So
I should check that.
Because if it isn't, then like there may be there's that's a correlation that's in there that you may sort of be missing, and that could contribute to the whether you get the temperature inversion in the disk.
Yeah. No, that's a very good point. Yes. Yeah, I need to check that.
We can talk.
No, but that's a very good point. Yeah.
Okay, Yancy.
Yeah, thank you very much for a very nice talk. I have two questions about the pre-stellar phase. The first one is, have you tried to also compare your abundance ratios? Because there have been several detections, and I know you talked with Sam this morning. And Sam in her 2021 paper finds nice consistency with a lot of the complex organics observed during the pre-stellar phase with the low mass protostars. And it seems like this would continue into the high mass protostars. I was curious if you had checked that connection yet.
Yeah, so I was talking with Sam this morning, and actually I think that's super cool that they are very consistent basically across all these different stages, and it kind of probably even comforts more that these molecules should be forming in ices in the pre-stellar phase.
Right.
Yeah, but it was really cool to talk with Sam this morning. You know, definitely that's a very good comparison to make. Yeah.
There's a lot of protostars I was seeing in Perseus, right, from Peaches, and then I was gonna ask you too, the NGC 1333A or something. It looks like it's actually down a little bit from the trend, and I was like, that's interesting because we have some I looked at pre-stellar cores in that same region and finding like super high methanol abundances that would, well, this is obviously for, this is for the CN.
Was it an interesting issue?
Is it in this plot?
This one?
No, I don't see it in this plot. Is it?
Maybe it was the first. This one, maybe.
The other one, I think, is in 1333, right?
Yeah, this one.
Yeah.
Is this for nitrogen bearing species?
Yeah,
it's a little bit below the.
Okay, so it's not in this plot, but
No,
It's
it
there.
is.
It's the blue one.
1333.
Oh, this one, right.
Yeah, so it's a little bit lower, which I find interesting, but again, it's for the CH3 CN, which I wonder, anyway, we could talk more about it later, but it would be interesting to do a Perseus comparison because it seems like there's a lot of protostar detections in Perseus.
Yes, but then the problem with those at the moment, I think, is that they don't go deep enough to see. So like the CH3CN values there, or I don't think they have HNCO, but the CH3CN and methanol, they have, I think, mainly the main isotopologue. So they don't have the 18.
So you come into optically safe issue or something? Okay,
yeah, exactly. So that's the problem with that. So really in low mass protostars, these are the ones that I managed to find. Well, at the time that I was writing this.
Yeah, of course. I had the issue too, making my comparison.
Yes. Yeah. No, but that's really cool. This one I need to look into because,
I noticed that too. It's interesting. Anyways.
No, that's,
Okay,
So I have one more question, if it's okay. Okay, second question is, I really I agree with you that the pre-stellar lifetimes vary, and we found various evidence, especially from recent deuteration studies of pre-stellar cores, that that's the case. But one thing that I always have as the caveat, and something that we didn't get a chance to explore in Maria Galloway-Spritzman's paper this last year, just because we didn't have time, is if you vary the initial conditions, how much can that also account for the spread that you're seeing in your various line? And you've got sources here, especially from AlmaGal, that are coming from very different environments in the galaxy that might have very different C/O ratios and things like that. So I agree with you that pre-stellar lifetimes probably really are varying, probably by more than a factor of 2, actually, in reality. But at the same time, proving that chemically is difficult. So did you explore different chemical initial conditions and see how that would affect the timing of the abundance ratios?
Yeah, no, that's a good point. So that's something that I have not done, and it's okay. So it's actually one of the things that I was planning to explore, after my PhD. But also, it's something that we tried to do with a master's student. So we looked at a bunch of chemical models. We didn't change. So you mentioned C/O ratios. We didn't change the abundances necessarily yet, but what we did was to change the temperature and the density, the initial physical conditions in that sense. And yes, we definitely see some scatter, but I think we still don't have a one-line conclusion for me to say it. But definitely they can change the scatter. As I said, I don't have too much attachment to the idea of time. It can have an effect, but it's probably more of a pre-stellar condition effect, as you say. Yeah.
Thank you very much.
Yeah, no, thank you. And also, actually, this time idea, I think it was also in one of your papers that I do cite in the paper. Yes, it's already. It's not a completely new thing. It was already mentioned before in the literature you were one of the people.
Any other question? Actually, I have a question. I'd like to go back to the point that Caitlin made about the high mass definition.
Yes, yes.
So when I look at the ultra compact H2 regions
Yes.
at such similar distance in 1 arc second,
Mhm.
there are more than tens of stars sometimes.
Oh, really? Oh.
So like 5 kiloparsec, you can see that 1 arc second how large that is. Luminosity is dominated by massive stars, but there are multiple massive stars within that 1 arc second, could be within that 1 arc second resolution. So when you cite that, I hope you have that in mind. So that's why I think it is better to define maybe high luminosity cores or something like that instead of high mass protostars.
Sure.
They're not it's likely high mass there are,
Yes.
but you don't know exactly what mass they may be and how many of them there are. So even in 1 arc second, 5 kiloparsec.
No, I completely agree. Also, I think another issue mainly on so here maybe not too much of a problem, but in the final plot that I showed for where the models can't explain the data.
Yeah.
Another problem is that the luminosity measurements, which are basically the same luminosity measurements I use here, are so the initial luminosity measurements were made based on a 15 arc second beam. So there are a lot of protostars there. And then we sort of correct it. So what we do this sort of 0th order almost approximation where we just say, okay, with ALMA we are seeing this many continuum bright sources, and then we just normalize that luminosity based on the continuum fluxes. Again, that could also not be the best way to do it. But this is what we have. But I mean, I've been talking with people, and apparently there is going to be soon good measurements of luminosity of these sources in the literature. So it would be nice just to see if that can maybe explain some of the spread we see there, or also even here in this plot. Yeah. No, definitely. Completely agree.
Okay, Feng has a question.
Yeah, thanks, very nice talk. So I was wondering how the GEMS observations of ICES can really confirm your finding. Are we looking for constant abundance there in ice species, or are we looking for other evidences?
Yeah, so that's a very good point. So obviously, one of the main things, so Evina, I think, has this GTO program with JWSC that I think one of the main things that they want to do is to really look to see if they find any of these complex molecules in ICES. And they, and so the problem there would be for these amber incomes, if we can detect anything, it will be like the most abundant one, probably CH3CN or HNCO because of the sensitivity problem. But maybe we will be able to see some of the over incomes. And there is a tentative detection of some of these over incomes in the JWSC paper, Corinos. And then in terms of the methanol, yes, definitely. Again, another thing is just to see if what I said, that this can lower the temperatures, we would expect seeing these molecule, methanol at least, in ICES toward the sources that they don't show methanol emission in the gas at millimeter wavelengths. So yeah, definitely JWC is going to be quite good in those. Did I answer the question?
Any other question here? Or no? Yes.
Yeah, following up on that, I think Yao Lun had that was the paper, right?
Yes.
The JWSC
Yes.
with the protostar.
Yes.
Did they compare to the gas phase? Because they detected methanol in the ice.
Yes, but I think, to be honest, I was trying to find.
It was like a weird protostar, or something that.
So I was trying to find. Yeah, I need to look at that paper in more detail.
Because it would be interesting to do a comparison.
Yeah, definitely. I think it would be very interesting to do. But I don't know if they actually went into the detail of properly finding the colonicity for those tentative.
Yeah, it was more like a hey, look at the spectra type paper. But
yeah, I think they probably are going to follow up on that. And but I need to look into the paper in more detail. So, but that would be cool.
Any other question? I have one more question.
Yeah.
I don't understand your envelope only model. For that envelope only model, is there a density distribution that you particularly used, or is it uniform? It can't be uniform.
Yeah, so for the envelope, I just assumed the power law density.
Okay.
Yes.
Okay.
And I think the power I assumed was 1.1 minus 1.1. Yeah, that's what I did. Yeah, it's very simple.
Yeah.
Yeah, I should also say these models are probably like very, initial models that they can be much better. Yeah, but maybe could give good estimations at this level.
Okay.
Yeah. No,
Any other last call? Any other question? Okay, let's thank Pooneh again.
well, thank you. Thanks so much. Yeah.
And see you next week.